Welcome back to ECE 320A. Homework 2 is due in a week, and that's covering all of Chapter 10, or the remaining part of Chapter 10 and some of Chapter 11, a fair amount of Chapter 11. Exam 1 is a week from Thursday, and that's on the 26th. That will be in class, and I didn't have a chance to do that this morning, but I will try to make a section on D2L containing exam number 1 review material, old exams, etc., so that you can practice. And I'll try to post exams that don't have any answers on them. You can look at it blank and try to respond to those, and then I'll give you also an exam with the answers posted in those. And there may be multiple answers for one problem or two problems. You just have to figure out a way to solve the problem that makes sense to you. As we said before we started, there is a voting form going around the classroom, and please vote for your preference or preferences for the exam review session for exam number 1. I have a full screen of goals. Let's see how far we can get. Today, we will quickly display and visualize the 4 different interconnections that we talked about before. You may not be able to frantically copy all of those down, but they'll be available in the notes, and you can then refer to those as needed. But then once we've looked at those interconnection structures, and those are all based on how the sources and the loads are connected, whether they are connected in a Y configuration or a delta configuration. We will then examine what we mean by the power in each of the phases, or a per phase power. And obviously then, if you can find the power in one phase, and if it's balanced, then you can just multiply that result by 3 to get the total power in the load, if you just have one set of 3-phase elements. We will then also talk about these concepts that may be a little bit confusing, but hopefully by the introduction of the pictures and the per phase power, it will make a little bit more sense when we talk about line currents and line voltages, or in voltages, when we're talking about that, it's line to line, transmission line to transmission line, but a lot of times we abbreviate that and just say the line voltage versus the phase voltage. Those sometimes are the same, they're sometimes different. Phase voltage and line voltage, and phase current and line current, and it depends on how your systems are connected, whether you're in Y connections or delta connections, and hopefully that will become clear. Then we will start to examine the analysis of these 3-phase systems by reintroducing the YY configuration, showing how we can identify the current in the neutral conductor. We'll state the conditions for a circuit to be balanced in a 3-phase setting, and then we will try to analyze or start to find some of these quantities, voltages and currents, in a 3-phase circuit based on a single-phase equivalent circuit. That's the plan. Let's then get started with some of these interconnection patterns. This one was presented the last time, I believe. We have 3 sources, A, B, and C. We have their potential generator impedance. Those are the Z sub G's. We also might have transmission line impedances in the 3 transmission lines. Those are the Z sub L's with the A, B, and C subscripts. And then we have loads on the Y-connected side of the load, ZA, ZB, and those are capitals, Z sub C. That's the YY configuration, and you could analyze that in all of its glory by simply performing 2 mesh analysis problems. You can see that directly, I hope, correct? So you could solve for different currents in this configuration by simply writing two mesh equations. But that gets pretty involved because now it has 3 sources, 9 impedances that you would have to keep track of, and there are ways to simplify that by looking at a balanced system. But that's the YY configuration. Compare that with the YDelta configuration, and now the load, and I had to erase, start over, recopy. That's now a delta on the right side. Hopefully that looks like a delta. Maybe it's not upright, but you can see the delta. The Y source is the same, but now you can see that we have a lot of the same structure on the left through the transmission lines, but once we get to the load, if somebody covered up that load side and you just saw the terminals A, B, and C that I've sort of duplicated, you couldn't tell whether that was delta connected or Y connected. And you may not be able to know what your load is. You may just be given line voltages, transmission line currents, etc. And we'll get into that in a minute. But that's the YDelta configuration. As I said, I may not give you enough time to copy these down, and you could just quickly sketch the idea, hopefully. Here is a delta Y configuration. Hopefully I haven't left out any of the pieces. We have our generator impedances. Our sources are now interconnected in a delta configuration. Our load is the Y configuration, and the transmission lines obviously connect those A's to A's, B's to B's, C's to C's, and it should be clear that the first C was lowercase and the second C was uppercase, just by the way I said it. Probably not, but the diagram makes it maybe a little bit more clear. That is a delta Y configuration, and you can see that we can still, whoops, made a mistake, didn't I? Fell asleep. But at this point in your academic career, you should be able, more than able, to identify mistakes in the textbooks and mistakes in my notes. And you could then say, that's not quite right, is it? I would think it would be this. That's where you're headed. You need to be able to do that or identify that. In that case, I had my line current in the B phase incorrectly labeled because I was doing it in a hurry. Lost 90 points out of 100. Failed that question. That'll give you a sense of my generosity in grading. Just to reassure you, comfort you going into exam 1. Okay? Oh boy. You guys aren't very, well, you don't appreciate that joking, I guess. Here's a delta-delta configuration. And maybe it's not that easy to get on the full screen, but I hope you can see that the source or the generator side is again a delta. The load now is a delta. And if these transmission lines actually didn't have any impedances, it wouldn't be too hard to find the currents in your loads, would it? Because now your sources would be immediately parallel to the different phase impedances at the load side. You could go from little a to little b directly over to capital A, capital B if those transmission line impedances were 0. And now that would be an easy problem to solve. It's not that hard to solve here, but it's a little bit involved. Now it would be nice maybe, and this is where we're headed, is if somebody started with a YDelta configuration, maybe it would be nice to just transform that delta set of impedances into a Y configuration, and then we have a YY configuration. You see how that could happen? And it's going to be important then to be able to make these transformations, to not only transform impedances from Y to delta or delta to Y, but also sources to convert those between delta to Y. And we need to find these relationships between Y and delta quantities. Let's then start that process by examining the YY configuration, or the load power for the YY configuration. And now if I ask you for the A phase power at the load, what would you tell me that would equal? Or could you give me an expression for the complex power associated with the A portion of the load impedance? So now what I want, so the response was accurate if I wanted that big of a answer. I was trying to be more specific. I want to know just at the load. So if I went just to the load terminals, capital A, capital B, capital C, I want to know what's the complex power absorbed by the A phase of your load. So just at the Z sub A element. And how do you deal with complex power for a generic element? What's our formula? That was the first formula on your crib sheet, I think. Haven't we referred to it that way? So it's P sub A plus JQ sub A in rectangular form. So I wasn't very specific in my question, was I? In terms of voltages and currents, what's the complex power in the A phase? Now I'm looking at the following. I want to know what is S sub A and I shouldn't have circled B. Boy. I just want to know what is that. I want to know what's the power, the complex power associated with that piece of the overall system in terms of currents and voltages. What do I need for complex power? Just rattle it off. What's the formula? VI star, right? VI conjugate. Now all you have to do is identify the appropriate V and the appropriate I to find S sub A. In this case, what voltage do we want? The voltage across ZA, which we have not labeled, but that's what we want to label, and this is actually going to be called the A phase voltage. This is the phase voltage at the A terminals of the load. So that's V sub AN. That goes from terminal A, capital A, down, if you had a voltmeter, from there down to capital N, the neutral terminal. So that now we have part of this equation. We now have V sub AN, and that's a phasor. This is actually the phase voltage in this particular circuit. That's the voltage associated with the A phase. That's a phase voltage. So that's the voltage across Z sub A, or the A phase impedance. That's the voltage across the A phase impedance. That's the phase voltage. We want to multiply that now by the current through that element, its conjugate, its complex conjugate. And that one's already labeled for us, isn't it, in the diagram? That's simply I sub AA. That's the current going through the A phase's transmission line. And so we might call that a line current. We now know that this is going to be I sub AA as a phasor conjugated, where this is what we will call a phase current, and that's equal to the current through the A phase impedance Z sub A. And in fact, this particular interconnection structure, that's equal to the transmission line current in this YY configuration. Now, if somebody goes out here and gets a little bit slap happy with their voltmeter and they measure voltages and they put their negative probe not at capital N, but they put it at capital B, and they say, oh, here's a voltage. What have they just measured? Now they've placed their voltmeter positive to negative between A and B. I hope it's clear that that's not the same thing as V sub AN. But V sub AB is called the line voltage. For short, it's actually the transmission line to the transmission line voltage. And you need to make sure that it's clear that you know the difference between phase voltage and line voltage. In this configuration, the phase current is in fact the line current. But let's now just make that observation. Whoops. Down here, let's just say here is a note, and that is that V sub AB is not equal to V sub AN in this YY configuration, in this Y connected load, essentially. V sub AN was the phase voltage, V sub AB is actually the line to line. That's from transmission line A to transmission line B, that voltage. And a lot of times we will get lazy, or everybody just calls it the line voltage. And that's for the Y configuration. Is that clear? How we would find the per phase power, complex power, in this interconnected structure for this Y connected load. We just look at the voltage dropped across the A phase impedance and the current through that A phase impedance, and then plug those into our standard formula, VI star. If somebody said, I want the total power, now I'm going to have to get a little bit creative, but I have infinitely tall paper. You don't know what's below, so you can just keep writing, right? You haven't squeezed in this Y delta. But if I wanted now the total power, then my total power at the load, let's say total load power, would be the complex power of the A phase, it would be the complex power of the B phase, and it would be the complex power of the C phase, and that was supposed to be a capital C. If this is a balanced configuration, what do you think's happening in those three phases? They're the same. So this would be 3 times S sub A, or we may just say forget the phase and just call it, or don't label it with a specific phase, just say it's the phase power, S sub phi. That's supposed to be a phi. That would be the total load power for that interconnected system. So if you can find one phase's complex power, which you know how to do, VI star, if it's balanced, then just scale it by 3 and you've got the total load power. That's the Y configuration. If we want to look at the YDelta configuration, again, I cheated and had this already written down, but you can leave space in your notes. Now suppose that I want the A phase power in this delta connected load. This is now the A phase, and here, oh, this allows for really nice word problems. And that's not a generic A, that was the A phase. So that's the A phase load power. It's not A load powers, where that A load power could have been the B phase. So you really have to watch how I'm reading that or stating that. If it's not clear, then you label what you're doing. You're saying, I'm finding the power in the A phase of your load. What's the formula now in this configuration for the A phase load power? Anybody brave enough to venture a guess or a correct answer? What's the idea? What did we do last time? If we say, wait a minute, this is quite a bit different maybe, but what did we do last time? We looked at the A phase impedance. Then we simply had to identify the voltage dropped across that A phase and the current through that A phase. And then we had our formula, or the variables that we needed for our formula. If we do this similar kind of thought process here, I'll make this a little different. I'll make it blue since we had yellow before, because this is not quite the same. There's our A phase impedance at the load. What's the voltage dropped across that element? So one of those was the phasor bar. Boy, this is getting more and more challenging, isn't it? I knew I should have paid more attention in my art class. Finger painting, that's the only one I enjoyed, right, in art. Very abstract. Yes, sir. So the question was, what's the difference between ZCA, it has an A in it, and ZAB, it has an A in it. I'm going to use the one that has the leading A in it, and that's just by convention. The A phase is going to be ZAB, then what's the B phase? ZBC, and the C phase will be Z sub CA. It's just convention. Okay, so we're going from A to B, that's the A phase, but that's a good question, it's a valid question, because there's two A's floating around. But that's my impedance that I'm wanting to know its power. So that now if I'm calculating the A phase load power, I now have the voltage. Ooh, that's not the same variable, is it, as the last one? But this is a different configuration. This is a delta configuration, and the voltage dropped across that impedance is now, that's my phase voltage, But it's also my line voltage, isn't it, in this delta configuration. So the phase voltage and the line voltage are the same in this delta configuration. What's the current through that element? Does it exist in my diagram right now as a label? No, I haven't labeled it, have I? The current that I need actually needs to go from capital A to capital B terminal, and that's now my phase current. That's not the same as my line current in this configuration, is it? So things have changed. But this is now the current that I need because that's the one that belongs with that particular piece of the A-phase impedance, or for the A-phase impedance. Is it clear what we're pulling into this? In this formula then, V sub AB, we just said that was the phase voltage, but that's also equal to the line-to-line voltage. Now do you see how you could really get confused if you're not paying attention? Because that's not the same as the phase voltage in the previous problem. This particular current is the phase current, but that one is not equal to the line current in this configuration, meaning I sub AB, just by the labeling, is not the same as I sub AA. That's what we're meaning. And this is true for the delta load configuration. But if I now have a per phase or the A phase complex power, it's not that hard to find the total power in this load, is it? Or set of loads, depending on how you refer to it. The total load power it's a complex number. That's now S sub A plus S sub B plus S sub C. But if we're in a balanced configuration, that's just 3 times one of those phases, which we might just label S sub phi. And that's our total load power. And here I'm even being not as descriptive and leaving off the total load complex power or total complex load power. I'm leaving off the complex. That's just implied. Questions on that? It should be clear that it might be important to know about delta to Y and Y to delta conversions. And I'm assuming you already have memorized all of ECE 220. So you know exactly where that relationship exists relative to impedances. For impedances, you could refer to, let me see if I have that here. I have to cheat because I haven't taken 220. That's on page 326, or that's in section 9.6, and those equations, and if you were That's really just a generalization of the earlier all-resistive network, which was way back in chapter 3, and that was on page 71 in section 3.7. And in chapter 9, I hope you will find the equations to go from delta to y. Those are equations 51 through 53. And to go the other direction, if you started with y-connected loads and you wanted to get a delta for whatever reason, now you're looking at the next three equations, which are 954 and 956. We also might want to understand how to convert sources between a Y configuration and a delta, or from a delta to a Y. It might help us in our analysis. And that's what we will subsequently derive, is how to relate these voltages between the two different configurations, the Y and delta, or the delta and the Y. So let's look into this process of analyzing these three-phase circuits. But before we do, let me just make sure it's clear, and you can keep me honest on this. The notation that I've been using is that I have a double subscript notation. For example, I might have V sub A, B. Then the voltage drop is from the first subscript, so you would go to the capital A terminal and measure that, put your positive ohm meter there, lead of your ohm meter, and then the negative ohm meter lead would be on the capital B terminal. So your voltage drop is from the first subscript to the second subscript. If I had currents, then the current is flowing from the first subscript towards the second subscript. That's the notation that I will be using. Now, to analyze these circuits, it's nice to be able to do the following, and the following is to be able to make these complex three-phase circuits, boil them down, or to find a single-phase equivalent. So let's look at this three-phase to one-phase equivalent. And we will do that for the YY circuit. Now, to begin that process, I need you to help. So what I want you to do is I want you to find I sub 0, which is the current in the neutral conductor. Well, maybe before we do that, I'll just give you the following quiz. I'll say, here's your quiz for today. Write a KCL equation. At node N. And now let's go back to our YY circuit. Ooh, and let me go ahead and put in a neutral conductor. And now what I'm asking you to do is I want you to write a KCL equation at node N, little n. And now I've highlighted or emphasized that with this dashed line. Write down a KCL equation at n. And like before, you'll need to turn that in to receive all possible points. Are we finished? Did you do it the short way or in the non-long way? What is the KCL equation at node n, which we may actually refer to as our reference node? If we just did it the short way, we could write it in terms of these line currents, couldn't we? The currents in our 4 transmission lines. And KCL says the algebraic sum of our currents need to be 0, or currents in equal currents out of a node. Currents in to little n, we just have the one, that one's blue, I sub 0. The currents out are the green currents. IAA, IBB, ICC. That would be the short answer, and you would get 2 points out of 100 for doing that. So now you have I sub AA. Oh, I can sign drop forms after class. Just teasing with, just playing with. There's 2 points. Now we need to get 98 more, right, for this problem. How do we do that? Now we want to rewrite these in terms of the voltages. And let's use terminal, thank you. Wrong diagram was the point. Let's use this guy as our reference. That's our reference node. And now I could say, well, what is I sub 0 in terms of voltages? And I haven't even labeled one of them, but if I use my double subscript notation, and if little n I just assumed as 0, I would add capital V sub capital N divided by Z sub 0, and that would be I sub 0. Is that clear? If my reference node, so now I have my ohm meter negative probe on little n, and I'm now just touching all the other points in that circuit with my positive lead. And the first one I'll touch is capital N, and that will give me V sub capital N. And that's the voltage dropped across Z sub 0. Then I'm going to touch that next one at V sub A prime N. Then V sub B prime N and V sub C prime N. Meaning, now I can rewrite this as there's I sub 0. What's I sub AA? Boy, good thing we had our Dramamine before class. V sub A prime in, because we want to assume all generality, so we'll assume that that generator impedance is non-zero, so we have to account for Z sub G A. But the drop across those three impedances in the A phase, Z sub GA, Z sub LA, and Z sub A, those are in series, so I can add those up pretty easily. That's my total impedance. And the voltage dropped across that is V sub A prime N minus V sub capital N. Yes? And I can do exactly the same thing for all of the other phases. So that now I have V sub A prime N minus V sub N all over Z sub GA plus Z sub LA plus Z sub A. That's I sub AA. I sub BB. And I sub CC. And that's my KCL equation. Did everyone get that? That red line is 98 points. The blue line is 2. Have to be fair. Yes, sir. So now the question was, why can't we set the neutral voltage to 0 when we're analyzing that? And basically, you are ahead of the game. That's what we're going to try to show. But now our reference node, little n, is what we're assuming is at 0 potential. Little n is maybe different, possibly, than capital N. So now what we're saying is, in all generality, we have several nodes in this circuit. The ones we want to concentrate on are A prime, B prime, C prime, little n, and capital N. That's now giving us our 5 nodes. One of those could be a reference node. That's our one that is shared the most, maybe, between all the others. And now we have 4 voltages to worry about relative to that reference node, little n. Does that help? We are distinguishing right now between little n and capital N. And we ended up with this equation. There is our KCL equation for this YY configuration in a 3-phase circuit. Now what I want to talk about is, what if we have a system that is balanced? What are the conditions for the system to be balanced? And let me just state those. We now have a few properties that a system needs to obey in order for it to be a balanced system. A 3-phase circuit will be balanced, or is balanced, if 1, V sub A prime N, V sub B prime N, V sub C prime N form a set of balanced 3-phase voltages. Did we define that one time before, didn't we? If I gave you a set of voltages and I said that set of voltages is a set of balanced 3-phase voltages, do you remember what that meant? How are A, B, and C, forgetting the n's and the primes, how are those related? How are their magnitudes related? Magnitudes are equal, aren't they? Phases are different, and they're different in a special way, aren't they? They're special. So they split this 360 degrees up equally. right? So they're 120 degrees apart. That's what we mean. They have the same magnitudes, but they are 120 degrees different in phase. And whether B is behind A immediately or whether C is immediately behind A depends on whether we have a positive phase sequence, ABC, or a negative phase sequence, ACB. Either of those phase sequences form a set of balanced three-phase voltages. We just have to know which one we're working with. But positive and negative can be okay. So that's one property. The second property is we need all of the generator impedances to be equal, which in our diagram, that's Z sub GA, Z sub GC, and Z sub GB are equal. And we can sort of carry this process further. We can say the transmission line impedances in each phase need to be the same. And that was this Z sub LA, Z sub LB, and Z sub LC. And finally, we need our loads to be the same. That now gives us a balanced three-phase system. Under those operating conditions, or with those properties in our system, let me state the following fact. If we have a balanced system, three-phase system, in that YY configuration with these four properties, then I state that we can actually claim that V sub capital N is actually 0. Do you believe me? And don't say, yeah, because you're in front of the classroom. That's not the right answer, is it? We can prove that to ourselves. And I know that if you're at this point in your academic career, you've just eaten alive all the math courses, so you've done all of these proofs. You just love those. So let's do a proof, just to bring you back to someplace nice and comforting, right? Makes you feel good, these proofs. I'm getting tired, so I'm going to minimize my writing. I'm going to call Z sub phi, that's going to be Z sub A plus Z sub LA plus Z sub GA. And that's the same if I put B's in every place. I'm just going to refer to a impedance per phase as Z sub phi. If that's the case, then I can rewrite that KCL equation. I can pull over, if you look back at this formula, I have four variables there, V sub capital N, and then I have my A prime, B prime, and C prime. Let me keep my primes on the right, and my capital N's, let me pull those to the left. So I have a V sub N over a Z naught, and then I have 3 V sub N's over Z sub phi. Those will form the left side. And I just have the right side remaining, meaning I now have V sub N times 1 over Z sub 0 plus 3 over Z sub phi. Since they were minus signs, I can add those to both sides and they'll be gone from the right-hand side. And then what's left? Well, I have a V sub A prime n plus a V sub B prime n plus a V sub C prime n all over the same denominator. And what do we know about a balanced set of voltages? They sum to zero, don't they? Because of their spatial relationship. Same magnitude, different angles. But those angles are 120 degrees apart so that they, head to tail, end up getting us back to zero. All we have to realize is that this piece right here is not equal to zero. We can divide that out, and now we can conclude that V sub n is equal to zero, and that's the fact that we wanted to prove. We can now say, okay, we finished that piece. Here's my finger painting. Oh, I should have used a different color, made it a little bit more interesting, and then I could have taken it home to Mom. Brother, long day. It's only half over. Where were we? We're analyzing three-phase circuits. You should just be getting really warmed up and excited. But this now allows us to make several different, or a couple of different observations. What if we go back to our YY, now I have to find it. We assumed little n was zero, didn't we? As far as that was our reference voltage, that was zero. We've just demonstrated that capital N's terminal is also zero. That means we have 0 volts across that neutral conductor. Zero volts across a conductor means we can fall down, but besides falling down, what can we do? We can make two different assumptions, can't we? We could say there's no current, or there's no impedance through there. Since there's no voltage drop, that could either be replaced with a complete short circuit, or we could remove it completely and have a complete open circuit. We could do either of those since there's 0 volts between them. So those are our two options, but hopefully that's clear from this diagram. The fact that V sub n is equal to 0 says that there is no voltage that's dropped between the source neutral which we were referring to as little n, and the load neutral, which we were referring to as capital N. And if there's no voltage drop between 2 points, there's no potential, there's no current flowing, is there? There's no current flowing in that neutral conductor. And that gives us the two options that I'd referred to before. Now we can either remove that neutral conductor or we can simply short those two terminals out with a short. We can replace the neutral conductor with a perfect short circuit, or Z sub 0 is 0, or that's what we ended up with, V sub n bar equaling 0. Well, if that's the case, if we now have V sub n equal to 0, does that help us with finding some of these currents? This is our KCL equation, and now we can just match up these three terms on the red equation right-hand side with the blue equation right-hand side, and we can find all three of these transmission line currents. And V sub capital N is 0. We've relabeled all the Z's to just Z sub phi. Now it's not that hard to compute the transmission line currents in this YY configuration for a balanced configuration. Our currents then can be determined. We have our I sub AA. That's now V sub A prime N minus V sub N over Z sub phi. But that's just V sub A prime N over Z sub phi. Likewise, we can use the B prime voltage to find I sub B A, or I sub BB. And the C phase. And now we can comment about these currents because we know something about the voltages. Z sub phi is the same in all denominators, isn't it? So however that impacts the angle, it's going to do it exactly in the same amount for all three phases. Meaning the current in each transmission line, which I'm just abbreviating to be line, the current in each line is now equal in amplitude, and if we remember, we're in sinusoidal steady state, so it's the same frequency throughout, probably 60 hertz in the US. But now they are related by the angles of our voltages, because the Z is going to just subtract off or add the same amount to each one. So however separated our voltages were to begin with, that's how our currents are now separated, relative. They may not be the same angle, but they will all be offset 120 from each other. So we now have all of our currents in each line. They're equal in amplitude and frequency and are 120 degrees out of phase with each other. So what? Well, that means you find one of those currents and you can find the other two, right? We don't have to solve for all three directly. If we can just find one of those, then we know the others' magnitudes are equal, and we just have to know, do we have an ABC or an ACB sequence, and we just offset our angles by 120 degrees from where we started. That means why don't we just work with one phase and not all three? And that's where this single phase equivalent idea comes from. If we have a balanced system, then we can essentially neglect two of the phases and just isolate on one in a YY configuration. That's what we want to look at now then. We want to look at this single phase equivalent circuit. And I think at this point you can now sketch it pretty quickly. There's our generator, which is now, let's say, VA prime N. Here's A prime, here's little n. Then we potentially might have a generator impedance between A prime and A. We might have a transmission line impedance, Z sub LA, and we might have a load impedance, Z sub A. And now, aren't you glad that you did well in 220? Now all you have to do is solve this single mesh equation. Chapter 9 for I sub AA, and now you've graduated up 2 chapters, and now you're doing three-phase circuits because you know the relationship between those in a balanced configuration. Now, what you need to keep track of is this is now the neutral conductor with no impedance. That was resulting from our determination that capital V sub capital N was equal to 0. But what you want to be clear on, here's where somebody could try to trip you up in an interview question maybe, is they might say, what's the current flowing in that neutral? And you go, well, from that schematic, I sub AA. But then you go, wait a minute. What did he ask? Did he ask for the current in that circuit schematics bottom conductor, or did he ask me for the current in my neutral conductor in my entire three-phase circuit? Is there a difference? Definitely. In this one, you're just looking at a third of the problem, aren't you? This will have a current flowing in it, but this is a single phase equivalent. In the three-phase problem, you have IAA, IBB, ICC all flowing in that neutral conductor. And what did we discover was true about those three if we have a balanced system? They cancel, they offset, they're equal to 0, aren't they? But in this particular diagram, you're going to have current flowing, hopefully, because you're going to want to analyze the circuit. But that's different than the entire system with the three-phase combination. That's what I want you to make sure you're clear on. That I sub AA in the equivalent circuit, that's what I just sketched. That's equal to I sub AA in the balanced three-phase circuits. That's the whole point of this exercise, to find the A phase current, but you can't make the same connection with the neutral conductor. So the I sub AA, let's say the current in the neutral conductor, in the equivalent circuit, that's not the same as the overall current in your three-phase circuit's neutral conductor. Is not equal to the current in the neutral conductor in the balanced three-phase circuit. Because what's the current in our neutral conductor? It's I sub 0, isn't it? And that's just the sum of those three. I sub AA plus I sub BB plus I sub CC. And we know that I sub 0 is equal to 0 under what conditions? When we're dealing with a balanced circuit or a balanced system. Questions on that? Now, you know based on Chapter 9 and Chapter 3 how to convert your impedances from delta to Y and Y to delta. Knowing what we now know with the analysis, we know that the phase voltage and the line-to-line voltage or the line voltage in a Y configuration are not the same. Can we find a relationship between those two so that if somebody gives us one, we can immediately conclude what the other one is in a balanced configuration? Let's now look at relating those two voltages. Let's look at relating the phase voltage or phase voltages to line voltages. And to do that, let's just write a KVL equation to find the line-to-line voltage in terms of our phase voltages in a Y-connected load configuration. Let's look now at the line-to-line voltages. And now it is critical whether we are positive or negative phase sequence. Let's examine this to begin with, and you can do this tonight for the other one, for the ACB or the negative, but the positive phase sequence is what we will look at now. The diagram will be the same. Here's our diagram. Somewhere. Let me sketch it. Here's the A terminal, and there I have Z sub A, and then the neutral. Then I have Z sub B, and there's B, and then I have Z sub C, but we won't even really need that in our analysis. I know what's the A phase voltage in this picture. V sub AN, isn't it? It's from the A terminal, so that positive is all the way over to point A, capital A. What's my B phase voltage with the same notation, subscript-wise? And what's my A to B line voltage? That's right there, isn't it? And I can do all of the other labels if I wanted to, but I'm going to concentrate on those red ones. But if I just looked at the C phase voltage, that would be plus V sub Cn to minus across the C impedance, I could now say, oh, V sub BC would be that voltage, and then V sub CA, where's my positive? My positive terminal or my positive probe would be at the C, and the negative would be at A. That's now the complete parameterization of my Y-connected load. Now I want to relate my phase voltages to my line voltages. And to do that, all it requires is that I write a KVL equation. And that's going to say, let me start right here and walk around clockwise. So I'm going to go into the minus terminal of this air gap, V sub AB, between B and A terminals. Then I'm going to proceed down across the A phase. And then I'm going to go back to where I started. And I'm So everybody okay with the signs and that expression? I'm going into the negative sign of the way I've labeled V sub AB. That's now minus VAB. I go into the positive side of VAN, and I go into the negative side of VBN. That's my KVL equation. So that if I wanted to, I could now rewrite that. V sub AB is now V sub AN minus V sub BN. Now let me just make some parameterization. Let me just suppose that I'm labeling the phase voltages and I have a positive phase sequence. Let me just say that this is now some magnitude. I'll just say V sub phi, and let me make that one my reference. If that's the case, what's V sub Bn? And it's a positive phase sequence. Now you just have to remember your diagram. If you're walking around that picture, you go A, then you walk around and you hit which phasor next? B, so it's 120 degrees behind A. This is now V sub phi at minus 120 degrees, and V sub Cn, which we don't need in this first formula, is 120 degrees behind B, which is the same as 120 degrees ahead of A. But now let's just use that parameterized form for our phase voltages in this expression for VAB and see how that's related to the magnitudes and the angles of this phase voltage. Meaning we can now say that VAB is now V sub phi at 0 degrees minus V sub phi at minus 120 degrees. And now aren't you glad you know your trig and how to relate phasors, convert those into complex numbers? These are just magnitudes and angles. This is polar notation, but we can put that into rectangular form. We now have V sub phi. That's at 0, so that's just a real number, V sub phi. And now we subtract V sub phi times the cosine of 120 minus 120 degrees. And we also subtract J V sub phi sine of minus 120 degrees. Do you remember your trig? What's this guy? We go around 120 degrees, what's my real value of cosine of minus 120? That's minus 1/2, isn't it? What's this guy? Now I'm down minus 120 sine. That's negative, isn't it? Now I have just a complex number with known values. The v sub phi is in common with all of those. I now have 1 minus a minus, and I have a minus, so I have plus j square root of 3 over 2. Does everybody know what that ends up being? You can do that tonight at your leisure, but that's actually a magnitude of the square root of 3. And its angle, so that's square root of 3 v sub phi at an angle of an inverse tangent of the opposite over the adjacent. And that is actually this root 3 v sub phi at an angle of 30 degrees. And that was v sub AB. Meaning if somebody gives you v sub AN, and I'll conclude with this, let's say this is v sub AN, that was v sub phi at 0. Now we know that v sub AB relative to that is the square root of 3 bigger and ahead 30 degrees. And you know how the others are related because they're all 120 degrees apart. We'll pick up at that point on Thursday.